All right, this is the last question that I have on this particular practice exam, and it's fairly long. So we want to consider f of x equals 2x plus 3, whose graph is given below. So this blue line that I see, that is exactly the function f of x equals x squared plus 3. Sorry, not x squared, 2x plus 3. All right. We're going to do a combination of things. We're going to estimate the area under the graph using what are called ReimannSums. All right, and then at the very bottom, we're going to find the exact area using geometry, apparently. That's fine. Okay. So we want to approximate the area under the graph of f of x from x equals 1 to x equals 5. So let's see, what are we really approximating? Here's x equals 1 right here. So I have a point up here. And here's x equals 5. Okay, so I want to figure out what's this area. Okay, and I'm going to approximate it using n equals 4 rectangles and left endpoints. Okay, so what does that mean? Well, I'm going to break this interval up into 4 pieces. Right now I'm just visually showing you what we're going to do. N equals 4 rectangles, so I need 4 equally spaced rectangles. And we're going to use the left endpoints. So if I come up on the left, here's going to be one of my rectangles. Then here's another rectangle. Here's my third rectangle. And here's my fourth rectangle. So you can see I'm using the points on the graph that are going to become the left endpoints for my rectangle. And we saw in our textbook that this is going to end up giving us the height of our rectangles. So the first thing we're asked to do is find delta x. And we're reminded that delta x is equal to b minus a over n. Now this is actually something that you're going to want to put on your note card, because I'm not sure if the problems that I assigned tell you that in the directions. Remember, this is an exam that I gave in class instead of online. So I do recommend writing this on your note card. And let's go ahead and remind ourselves that the first value that we see is really our a value. So this is really a equals 1. And the bigger value that we see is really our b value. So that's really b equals 5. And then, of course, we're told what n is. So in this case, our delta x is going to be 5 minus 1 over 4. Well, that's 4 over 4, and that is 1. Okay. So our delta x is 1. Okay. Next, it says draw 4 rectangles on the graph. Well, I actually already did that in red. And we want to give the x sub I value for the left endpoints of each rectangle. So what we're really asking for is, what is this x value? What's this x value? What's this x value? This one. And there's 4 of them, right? So hopefully you can see where these are going towards. Those are our left endpoints. So we could visually look at our drawing and figure out what they are, but the other way to do it is you create your subintervals. And your textbook went over this. I know it can be a bit confusing. How you start your subintervals is you start with the value of a. Remember, a is 1. So we're going to start at 1. And then you add your delta x. And you're going to do that each time. So 1 plus 1 is 2. That's our first subinterval. Then we start back at 2. 2 plus 1 is 3. That's our second subinterval. 3 plus 1 is 4. That's our third subinterval. 4 plus 1 is 5. That's our fourth and last subinterval. So if you've done this correctly, you should notice 2 things. The number of subintervals should be the same as n, and the very first value should be A, the very last value should be B, if you've done it correctly. And now it's really easy. If we want left endpoints, we literally take the value on the left for each of our subintervals. And that's exactly what we saw on our graph we would label. x1 is 1, x2 is 2, this is kind of boring, huh? x3 is 3, and x4 is 4. Okay, so those are our x values for our subintervals. And of course up here we had our delta x. So now we need to approximate the area under the curve using a Riemann sum. And then I remind you what the Riemann sum is. Now again, you're going to probably want to put this on your note card because I'm not sure the online directions will give you this information. Okay, now this particular formula is for n equals 4. If n equals 5 or n equals 8, then you would have 5 or 8 values accordingly. Okay, so let's put all of our pieces together. It's telling us to approximate the area, and it tells us that our area is approximately, notice the parentheses here. Okay, I'll erase that, but hopefully you can still see them. The parentheses are going to go around f of x sub 1. X sub 1 is 1, plus f of x sub 2, which was 2, plus f of x sub 3, which is 3, f of x sub 4, which is 4, and I'm going to multiply all of that by delta x, but delta x was just 1. So how do I find f of 1, f of 2, f of 3, and f of 4? Well, I know what f is. Whoops, don't forget the 3. All right, f of x is 2x plus 3. So what are we going to get? Well, if x is 1, 2 times 1 plus 3 is 5. If x is 2, 2 times 2 plus 3 is 7. If x is 3, 2 times 3 plus 3 is 9. If x is 4, 2 times 4 plus 3 is 11. And you'll notice a pattern, and that's awesome. Typically, you'll see a pattern. So we have 5 plus 7 plus 9 plus 11 times 1, and that is going to give us an approximate area of something exciting. Let's see, 9 and 11 is 20, 5 and 7 is 12, 20 and 12 is 32. All right, so we get the area is approximately 32. Okay, the last question, find the exact area under the graph, the integral from 1 to 5 using geometry. Okay, so I'm going to actually do this two ways. I'm going to do it using geometry, and then I'm going to actually also show you how to do it using what we already did a bit of practice on, integration. Okay, so let's start with geometry. All right, if we come up here, we're looking for the exact area now. I'm going to go ahead and erase what I've drawn on our graph. Okay, let's go ahead and erase this stuff, all the extras. What is the geometry that we are looking at here? I guess I can erase that too. Well, we're still going in between the value of x equals 1 and x equals 5. So if we look at the geometry shape here, we have a trapezoid. So some of you may know the formula for a trapezoid, for the area of a trapezoid, and if you do, that's great, you can use it. Most of us don't remember what that is. So instead, we can break this up into two different shapes. We have a rectangle and we have a triangle. So how do we figure out the area? Well, the exact area is going to be the area of the triangle, plus the area of the rectangle. So what's the area of my triangle? Well, the area of the triangle is going to be, we know, it's 1/2 the base times the height. So what's my base? Here's my base. And notice it's x equals 1 to x equals 5. Well, that's 5 minus 1, which is 4. So my base is 4. What's my height? My height's a little harder to figure out. So I'm going to pause on that. Let's look at the rectangle. And that'll help us actually with the area of the triangle above. So the rectangle, we know, is just going to be base times height. The base, of course, is 4. It's still a distance of 4 between these two. What's my height going to be? Well, the height of this rectangle is going to be f of 1. Because the height goes from x equals 0 all the way up to this point right here. And if I want to find the y value of that point, I need to evaluate my function when x is 1. Well, 2 times 1 plus 3 is 5. So that means my height is 5. And of course my base was 4. Sorry, my pen's acting up. That's a 4. Okay, so how does that help me with the height of my rectangle? Sorry, the height of my triangle. Well, now I know that starting here, this is on y equals 5. So what's the difference? If I start at 5, how far do I have to go up? What's this value? Well, this value is going to have a value of f of 5 from x equals 5. Well, what's f of 5? F of 5 is going to be 13. 2 times 5 plus 3. So if I'm going from y equals 5 to y equals 13, I can find that height by subtraction. 13 minus 5 is 8. So my triangle has a height of 8. So the area is going to be the area of my triangle, which is 1/2 times my base of 4 times my height of 8, plus the area of my rectangle, which is going to be my base of 4 times my height of 5. Okay, so let's multiply everything together. 1/2 times 4 is 2, 2 times 8 is 16, 4 times 5 is 20, and 16 plus 20 is 36. So that's the exact area using geometry. We should get the exact same answer if we use integration. So let's do that. It wasn't part of the original directions, but this is still good practice. What if we did regular integration from 1 to 5 of 2x plus 1 dx? Well, finding my antiderivative, the 2 stays, my new x power is squared, I multiply by 1/2, I'm going to add x, and I want to evaluate this from 1 to 5. Well, that's just going to be x squared plus x evaluated from 1 to 5. The fundamental theorem of calculus says plug in the first value, the top value first. So if I plug in 5, 5 squared is 25 plus my x value of 5. And then I have to subtract what happens when I plug in my lower value. 1 squared is 1, and 1 is just 1. So what do I get? I get 30 minus 2, which is 38. Exciting. That is not the same answer. Did I mess up somewhere? Let's see. 16 plus 20 is 36. 5 squared is 5. That didn't work out the way I expected it to. Why not? Let's see. Well, isn't that embarrassing? That's what happens when I try to do things on the cuff. These should be the exact same area. What am I missing? Okay, well, I'm just gonna have to pause this video so I can find my error.